Okay, in the last video, we talked about internal standards, abbreviated with IS, and we compared that against a surrogate, which is abbreviated as an SA. Both of these are unlikely found in samples, both of these are added in known concentrations, but the surrogate is added only to my samples, and the internal standard is added to everything that gets processed. The surrogates are typically added in the beginning of the process, and internal standards are typically added at the end of the process. Okay, so now we're delving a little bit deeper into the world of quality control and expanding our horizon of knowledge in the 115 class. Isn't that great? So here we have a summary. I have a summary. Why do I talk about myself in plural term? That's kind of scary if you think about it. All right, so internal standards, something added to all samples, something added to all standards. It should show up in everything, or at the report wise, it should be in every single report that we generate here in the very end of these what we call batch runs, and it helps ensure that the instruments are injecting the proper amounts each time. And that's kind of the key here, folks, right? We're checking the instrumentation now. We're not necessarily checking you. So surrogates, we're checking your process, and internal standards normally check the machine's capability, the machine's reproducibility, the machine's way of injection. That's really what we're looking for here with internal standards. All right, so now if I go back to this definition thing, I'm going to scroll down and take a look at some of these others. Oh my God, right? Look at all of these. We're going to talk about all the, not every single one of them, but yeah, we're going to talk about quite a bit of them. And today, what we're going to talk about is 3.12, which is calibration standards. And the reason I do this is because I just talked about calibration curves and I talked about calibration standards in the previous video. And you're probably like, what? What is a calibration curve? I don't know. Well, now is the time to talk about this and talk about the purpose of a calibration and what is a good calibration and what's a bad calibration. So if I look at calibration standards, abbreviated CAL, oh, go figure, rocket science, a solution that is prepared from the primary dilution standard solution, woohoo, fancy, or stock standard solution, and the internal standards and surrogate analytes. Oh, well, I just talked about that, right? So now I'm feeling fancier and smarter because I know what those terms mean. The cal solutions are used to calibrate the instrument response with respect to the analyte concentration. Again, if I told you to read this and I'd be like, memorize, you're going to look at this and say, what? What does that even mean? I don't even know, right? A solution prepared from the primary dilution standard solution or stock standard solutions and the internal standards and surrogate analytes. The cal solutions are used to calibrate the instrument response with respect to the analyte concentration. Okay, yeah, whatever. So we need to talk about what calibration standards are, what's their purpose, why do we do them, and so forth. All right, so let's say that I have a sample in a lab and the sample has now been processed and I've went through the method, the SOP, and I'm like, okay, here, it's ready. So this processing is now finished and it goes to some type of instrument most of the time or some type of process so that way we can generate some data. All right, so let's say that I get a report back and my report on the sample is going to be like, okay, the signal, oh gosh, my fingers are too happy today. I just keep moving this screen around. All right, so this signal is going to be like, okay, 0.538. Here you go. What do you want me to do with it? Right? A signal is a signal. A signal doesn't mean how much. A signal doesn't mean concentration, right? Most of our time, our job in a lab is to figure out how much is there. So a signal is not, it's not the same as a concentration. That is not what signals are. Now, sometimes machines are very nice. Sometimes machines will take signals and it will convert those into concentrations for us so we don't have to do any of the math work. Great, happy, we do it and we use it, but not in our lab. Because the reason is I want you to go through the process of making what we call a calibration curve and seeing how that calibration curve helps you determine how much is there concentration-wise. All right, so the idea here is if we run samples and we get these weird random numbers that we call signals, like how does that relate to a concentration? That is what this is all about. So let me give you an example. I go into the laboratory and let's say that I take some cereal from the grocery store and I crunch it up. And when I take that cereal from the grocery store, I process it. So I'm probably going to digest it. I'm going to heat it. I'm going to add some things to it to make sure that it can help dissolve. And the reason that I'm processing it is, let's say I'm going to look for the iron concentration in cereal, right? Because it's there. Iron is a fortified mineral. I can see it on the nutrition label. So I get to the instrument, I run these samples on the machines, and my machine says 0.538 absorbance. Okay, whatever that is, right? I don't know what that is yet. But either way, it's a signal. That does not mean 0.538 iron. Okay, this is just a value, and that value doesn't mean anything unless I do something with it. And the only way that I know what to do with it is establish what we call a calibration curve. That's what this is about. All right. So what would happen is that in a lab, if this is what I was looking for, I would want to focus on iron and I would want to make a series of standards. And standards are things with known concentrations. That's what those are called. So I've made it. I've done it. I know how much is there. I know how much I've added. So what will happen is that I will normally make a series of different standards. Typically, calibration curves are going to be 3 to 5, and 3 is the minimum that we can have. But 5 is always the recommended number of standards that you should make. That's because if one screws up, 2 points always make a line, right? So for instance, if I only do 3 standards and that's it, the point of this is to get some type of linear relationship most of the time. Well, if I delete one of the 3 points, I get 2 points now. I can draw a straight line through any 2 points. It doesn't make any sense. So that's why 3 is always the minimum. If you mess one up, you got to go back and you got to redo it. However, 5 is always going to be the recommended one, if not more. Your SOP tells you how many calibration standards to make. Your SOP tells you how to go about making those standards, right? It doesn't leave any math to you at all. It is literally step 1, step 2, step 3, step 4, step 5. Add this amount to that flask. Add this amount to that flask. Add this amount to that flask. That is what we're doing in the SOP. There's no questions in the SOP. As long as we can read, we should be able to do what they tell us to do. All right, so standards. Get iron, and I'm going to make a series of standards. And let's say I'm just going to use random concentrations here. I'm going to do a 2 part per million solution of iron. Part per million means a very tiny, tiny amount. So part per million is actually equal to milligram per liter. So a 2 part per million solution would be 2 milligrams of iron that's dissolved in 1 liter of volume of liquid. That 1 liter, think about half of a 2 liter at the grocery store, right? That's kind of the amount that we're talking about. So super, super tiny, small amount. 2 milligrams, little bitty flakes, get dissolved in a half of a 2 liter, a 1 liter volume. All right, so I'm going to make a 2, and then I could make a 4, and then I could make a 6, and then I could make an 8, and then I could make a 10, right? The lab directions are going to tell me, but this is the reason that we're doing it, because these are concentrations that we've made, and we know what should be there, and we're going to run these on the machines, all right? So what's going to happen is that I'm going to run a 2 part per million, And that 2 part per million is going to give me a signal. And that signal, if that's what we're using as an example here, is absorbance. All right, whatever. I don't care what the signal is. Absorbance, whatever that means. Who cares? It's just a signal. It's a number. So if we go up in concentration, look at this. 2 goes to 4. So if I'm doubling the concentration, my signal is probably going to double as well. And then I go 2 to 6. So if I do that, then here's 4, here's 6. Well, from the beginning, 2 times 3 is 6. So that means my signal probably will triple. And then here I have an 8, and I probably will get a signal. And here I get a 10, and I will get another signal. And this is what I would see on what we call a calibration curve. So what happens here is that we connect all the points, and hopefully a straight line goes through all of those points, including a 0, 0 piece, right? That's very important. This is where we start. We blank the machines out just like we tear out our balances, so I get a 0, 0 data point. So this is going to provide me a way to make a series of concentrations that drastically go up and up and up and up and up. I'm going to run those on equipment, get signals from them. I made them. I know what's there. And this should establish what we call a linear relationship. So my curve, for the most part, should be a straight line. If it's not a straight line, then that probably means I've messed up on the standard prep. And that means I probably need to go back and redo it all over. Without good calibration curves, you cannot do anything with your samples, anything with the surrogates, anything with the internal standards. You can't do anything at all. So calibration curves are at the heart of everything. All right, how do we know if linear is linear enough? Like, can I look at it and be like, yeah, that looks like a straight line, great job? No, we look at something called a regression coefficient. And this is an R² value most of the time is how we represent this. This is called a regression coefficient. This will be part of Excel. Whenever you do calibration curves in Excel, you can see that regression coefficient. We can get it to apply that to the curve that we make. This also shows up on instrumentation reports if we allow the instruments to do the calibration curves for us. But folks, this is what we call a calibration standards. So we are making something in the lab of known concentrations and we run them. What we hope to see is a signal increase. As we increase the concentration, the signals or the responses should go up and up and up and up and up. Most of the time, it should be a linear relationship, and this linear relationship lets me know, did I prep something the proper way? So there should be a cal curve, number 1, for all of the analytes that I want to measure. So in this particular example, I want to measure iron, and I'm going to make a standard solution of iron. I run these solutions or these standards on the machine and generate a curve. Great. That's what we do it for. That way, when I get a sample and my sample is 0.538, then what will happen is that I'll look at where does 0.538 show up here on the curve, right? Because if I can track this over and be like, oh, 0.58 is right there, then I can come down and it helps me determine the concentration. That is why we need the calibration curves made. It helps us to determine the concentrations of the samples. This converts the signal over into the actual amount of stuff that is present. All right. So number 1, it's got to be done with every analyte. So that means if my method has more than one analyte, I will end up with more than one calibration curve. So for instance, we do a lab on honey, and honey looks at 4 different sugars. Well, all of those sugars should have their own cal curve, every single one of them. So I'm going to make a set of standards that have those sugars in them. I'm going to run them. I'm going to build a cal curve for each sugar. So that way, when I run samples, I can take the information from each of those sugars that it sees and plugs them into the proper calibration curve to make this thing work the proper way. All right. Next up, I'm going to have to do it with the surrogates as well, because the surrogates, we need to know how much is there. We need to know what the amount is. All of that process has to take place accordingly and the proper way. So not only do surrogate analytes have to have a calibration or a calibration curve in order for you to solve concentrations, but there are some people that will also build calibration curves around the internal standards as well. So all of these things that you were adding into the sample in order to check quality of the laboratory workers, those also typically have to have calibration curves and standards made as well on the back end in order for you to calculate those concentrations as well. Because again, the idea is to pick out something, pick out a concentration that should match our expected values, make sure that those are showing up every single time in every single sample, and calibration curves will make very easy work of that. So just keep that in mind. Cal curves are not just for things that you're looking for, aka analytes, but they're also in addition to all the other things that you're adding into the solutions. Now, to be honest with you, a lot of times when we use internal standards in our lab, in our experiments, then I'm not going to probably make you use a calibration curve for those, and we're just going to look at signals from the equipment and signals from the instrumentation. As long as the signals are staying constant throughout the samples and the standards and everything else, if we don't see too much variation, then I'm typically okay with that. And some people are if they get that option, but others will have to build a calibration curve around the internal standards as well. All right, so if I go back to 3.12 when it talks about calibration standard, it's going to say, again, once more, we'll read it, a solution that's prepared from a primary dilution standard or stock standard and the internal standards and surrogate analytes. The cal solutions are used to calibrate the machine in respect to the concentrations of the stuff that you're looking for. So that is 3.12, which is the definition of calibration standards. All right, so if we need to sum it all up, calibration standards, abbreviated CAL, it establishes a relationship between the amount of stuff and the signal that you're getting from the piece of equipment. If more stuff is there, signal should go up, of course, and it should go up accordingly most of the time. So if you double the concentration, the signal should double. If you triple the concentration, the signal should triple. And it helps lab workers and people like us that are in there using the equipment to determine how much stuff is in the unknown samples that are given to a laboratory and responsible for us to determine how much is there. So again, the word stuff I just use for analyte. Analyte is more appropriate. Analyte sounds more, fancy, makes it sound smarter, but I like the word stuff. All right. So for instance, here, CFPUA, they will do a bromide method, and that bromide method is 300.1. So what they would do is that they would take drinking water samples, let's say from your tap water, they would analyze them using a piece of equipment. And that piece of equipment is going to look for bromide as one of the things in that method. There's a whole bunch of different ones, but bromide is one of that. So for instance, I need bromide standards. So in the laboratory, I would order a bromide solution that is already prepped and made for me. I would dilute that bromide down to various concentrations, and then I would run what we call those calibration standards on the machines, and I would get signals from them. And those signals should give me a linear relationship. That way I can use that to solve for bromide levels in the samples that are given to us in a laboratory environment. So it all starts with calibration standards. Very important to have those clean on hand. A lot of those calibration standards, they are ordered, at least the strong ones are. So the strong ones are typically ordered through third parties, and that could be through a company like VWR, it could be a company like Fisher. There's a whole series of different third-party companies out there that will make these standards or sell these standards to a company so that way they can use them to make their calibration curve with. All right? Okay, so again, that just sums up another definition for us. We're working ourselves through little bits at a time within this particular category. Again, I think it's the most important piece of the method as of right now, and it's just getting acquainted with some of the terminology. So in the next video, we're going to continue on with another definition, And we're going to pinpoint what that definition is going to be and that term's going to be. Very basic, very run-of-the-mill. Be like, oh, yeah, that's what that's called? Okay, yeah, I know that. But it's just a term that can throw people off if they're not very careful. All right, so I'll see you in the next video. And in the next one, we're going to talk about the term called Matrix. And no, I'm not talking about Keanu Reeves and the Matrix movies.